Okay, there's been some problems that have come up in ALEX that might be helpful to talk about. One of them has to do with this idea of electron affinity. So, electron affinity, and then also ionization. Okay, so these are the two topics we're just going to talk briefly about. Electron affinity deals with the attachment of an electron to the outer shells of a neutral atom. So let's take, in this case, let's take sodium. So you have sodium right here, and if we add an electron to that, then that will give us the Na minus, the sodium anion. Electron affinity, when we add an electron to a neutral atom there, that will release energy, and the magnitude of that energy is known then as the electron affinity, and that number will be in a table. It will be given to you in a problem. And so the opposite then of that reaction, just if we flip that arrow around, would mean that the sodium anion then giving us Na plus E minus, that would then absorb energy, and the magnitude of the energy that it would absorb would be that electron affinity. So when I'm tackling problems, I look for the neutral. Occasionally there'll be some tricky ones where they'll do a second ionization energy or something like that. But generally look for the neutral, find out what's happening to the neutral, and then look for how the arrow is pointing. I'll do some examples in a second. Ionization deals with the neutral, in this case sodium, taking an electron off, and it takes energy to pull that electron off, leaving the sodium cation plus an electron. So the neutral here has had an electron taken off of that. It does take energy. The system has to absorb energy. How much energy? What's the magnitude of that energy? Well, that's the ionization energy. Okay, and there might be an opposite reaction, just where we flip that arrow around and we have Na plus an electron will then lead to the sodium neutral. This then will release, it's the opposite reaction, it will release energy, and the magnitude of that energy is the ionization energy. Okay, so again, look for the neutral, find out what's happening to the neutral. And so let's do some problems. That's the only way to kind of understand this at times. So let's pull up an ALEX problem right here. The first one has to deal with germanium. Okay, so it gives us a table. There's electron affinity, there's ionization energy. Okay, so it has that. Let's start tackling some of these problems. Okay, so here is the neutral. Find that neutral, the neutral germanium. Okay, and we're pulling off an electron, so that does require energy to be put in. How much energy? Can we calculate that? Yes. That would be, if you remember our discussion, the ionization energy. And that will be 762. We'll put a decimal after that because ALEX likes that. Alright, that's the first of these. Now let's tackle the second one. Okay, this is germanium, the neutral. We're trying to stuff an electron on that, giving us the anion. This is the exact reaction that is an electron attachment. If you remember, that releases energy. Can we calculate that? Yes, we can. That's electron affinity. So electron affinity then will be 119. 119. Period. We should be able to check those. We should be accurate on those. And ALEX does say that we're right. Let's tackle some more. We have to see some more of these. We have to see when those reactions are flipped around. Okay, so in this case, we're talking about fluorine. So let's look at that first reaction right here. That's fluorine, the neutral. Find out what's happening to the neutral. We're pulling off an electron. When we pull off an electron, that's ionization, and that takes energy. Okay, so that's going to absorb. Can we calculate how much? Yes, we can. That's the ionization energy of 1681.0. 1681.0 kilojoules per mole. Alright, so here's a slightly different, find the neutral, different setup. Find the neutral. This is fluorine, okay, and we're adding an electron to that. This is on the right hand side of the equation to give us the F minus. This is the reverse reaction of an electron attachment. Find the neutral. We're trying to add an electron to that, and if you go back to our discussion that we had here, then here's the neutral. We're trying to add that electron. This is on the left hand side of the equation. And as we go back to our Alex problem, notice that that's on the right hand side of the equation. So electron affinity releases energy. That means this is definitely going to absorb energy because we flipped that arrow around. That's all we've done. Can we calculate that? Yes. That is going to be electron affinity, and that's going to be 328 point. Let's go ahead and check this. Make sure that we got the answer right. Every now and then my thinking gets wrong and I've got to just make a quick adjustment. So that one's correct. Let's go on to this third problem right here. Again, this is for copper. Okay, so find the neutral. The neutral's on the right hand side here. So copper is going to, we're pulling off an electron on the left hand side, leaving us with a copper +1 cation. This is the reverse of an ionization energy reaction. It's the reverse. And so if you remember from our discussion, then it takes energy to pull off an electron. Since this is the reverse, then this is going to release energy. How much energy is it going to release? Well, that's the ionization energy of 745.5, 745.5. And we're done with that one. Now let's look at this bottom one. Okay, so as I find that neutral's over here on the right hand side. That means a reaction has been reversed. And so again, this is copper. We're trying to stuff an electron on there, then leading to this copper on the left hand side. So this is a reversed electron affinity or electron attachment type of a problem. So a normal electron affinity problem releases energy. That must mean, since this is the opposite reaction, this is going to absorb. Can we calculate how much? Yes, we can. This is electron affinity, so that's going to be 118.4. 118.4. Let's go ahead and check our answer, make sure we got our reasoning right. Okay, and we did. So let's do one more just real quick. Let's go through this, find that neutral. Okay, so this is this strontium plus. We find the neutral. Okay, so if you flip that around, then you're going to see that that is the opposite of an ionization reaction, where we strip off that electron. So we're going to deal with ionization energy, and again, this is the opposite of our ionization down here on the bottom. Alright, so let's go back here to our Alex. So it takes a ton of energy to pull off an electron normally, so that would absorb, but since this is the opposite, we're going to release energy. How much energy? 549.5 is that ionization energy. 549.5. Okay, so let's go down. Here is the neutral strontium. We're trying to stuff an electron, trying to attach that electron to those outer shells, leaving us with the anion. This is just a straight up electron attachment or electron affinity problem. Those release, if you remember our discussion, they release. How much do they release? How much energy does it release? Let's go up and check that electron affinity, 5.03 kilojoules per mole. So 5.03 kilojoules per mole. Let's go ahead and check that, make sure that our thinking straight. We do. So these are doable. It just takes a little bit of thinking. As I was making this video, boy, I made 2 or 3 mistakes just because I wasn't thinking real well. And so know what an ionization reaction is. When we take a neutral and pull off the electron, that always absorbs heat. When we take the neutral and we try to stuff an electron into those outer shells, then that always releases heat, and this has to do with electron attachment, and we use those electron affinity numbers. I think this should help you tackle these problems.